Hi. In this webcast, we're going to talk about the kinetics of particle work and energy, lecture 14, conservation of energy. This will be our last session for chapter 14, where we're going to talk about conservation of energy. One of the example would be the pendulum. If you see the pendulum, it's moving in this direction. So it has a potential energy. If you take this position is a datum, it has a potential energy, and at the same time, the pendulum is moving upward. So there is a movement and there is a change in potential energy. And for this kind of combined scenario, we can apply conservation of energy. So let's see. What today's objective is. So we're gonna formulate the law of conservation of energy. Again, some other example is from the plane. These paratroopers is jumping. So when they were at the plane, they were not moving with respect to the plane. So they had some potential energy. For if you assume the plane if you assume this a plane, so plane is maintaining an altitude, so its gravitational potential energy is fixed. Once the paratroopers jumps off the plane, their gravitational potential energy is being converted to kinetic energy. So this kind of scenario and at the almost hitting at the ground, there's maximum kinetic energy, but zero or near zero potential energy. So there is a conversion between kinetic energy to gravitational potential energy. So this kind of scenario, we can apply the conservation of energy law. Also, similar to the pendulum, here you see the girl with the swing. They're swinging. She's swinging with the swing. She has a potential gravitational displacement, so she has constantly changing his position, and also he has a motion since she is moving. So there's also a kinetical energy and potential energy mixture. So in this kind of scenario, we can apply the conservation of energy law. Let's find the conservation. So derive conservation of energy. So conservation of energy. So to formulate that, we have to recall some definitions from previous lectures. So we know principle of work and energy. So if we have work done from point 1 to point 2, we have the initial kinetic energy plus the work done gives you the final kinetic energy. And in our just previous lecture, we developed the equation for conservative force, right? For conservative force, we had the equation U1 to 2 only for conservative force. We can say the conservative work done is equals to the potential function at position 1 minus potential function at position 2. So we'll start with the principle of work and energy. And this work here, we can say this is a combination of both conservative plus non-conservative let's use a different color. Non-conservative. So this energy from the work and energy principle, this U includes both the conservative work and the non-conservative work. So we can write this equation in this form. So T1 plus U12, which is for conservative, plus U12, which is for non-conservative, equals to T2. Now if we assume okay, let's plug in the conservative equation that we have derived from previous lecture. So U12 conservative equals to V1 potential function V1 minus V2. So we're going to replace this with V1 minus V2, which is potential function V1 minus V2. So this equation becomes T1 plus V1. If we take the V2 on the other side, we'll get U12 remains the same for the non-conservative. So T2 and the V2 goes on the other side, so plus V2. Now for circumstances, for a scenario, if we assume that if we don't consider the non-conservative work done, if we neglect this or doesn't consider into our system, this becomes 0. So the equation becomes T1 plus V1 equals to T2 plus V2. So this is our equation. So this equation is called conservation of energy. Conservation of energy. So what this equation tells us that during motion, the summation of the initial kinetic energy plus the potential energy equals to the final summation of the kinetic energy and potential energy. For this equation to be valid, we can see that there has to be a transformation of kinetic energy into potential energy or potential energy to kinetic energy to have this equation T1 plus V1 equals to T2 plus V2 be valid. So same way we saw some example in the previous slide when the paratrooper is jumping from a certain height, his potential energy is being transferred into kinetic energy when he's falling from a certain height. So this equation will be valid that when you there's a conversion of kinetic energy to potential energy. So now let's see an example. So let's assume the example of the paratroopers where we had the plane at a certain height flying, right? The plane. And here is our paratrooper at this height. So here is our paratrooper at the height of h from the ground. So that is our ground, and he is currently at this position. He jumps off the plane, and we just take a random position in the mid air, say about half of the height. So if we say the total distance is h, and this height is a mid air, so h by 2. He is still here, a little bit blue. So he is still here, and then the paratrooper, for example, at the ground when he lands, he will be here. So in this scenario, what would be so let's write down our conservation of energy. T1 plus V1 equals to T2 plus V2. So now let's consider the position 1 when he was at the plane. So he was maintaining constant height, so there was no kinetic energy. So at that position, his total mechanical energy. So total mechanical energy, energy E at position 1. So total mechanical energy E will be only the weight of the person. If we say it is W, which is the mass of the paratrooper and the gravitational pull mg. So if we assume weight is W, it will be W plus A multiplied by H, the total height from here to the ground, which is H. And there is no kinetic force because he's in the plane, so it will be 0. So total mechanical energy will be WH. Now assume that he jumped and he is falling, and now he is at position 2, where you have both, because he is falling. You have the kinetic energy and the potential energy. So at position 2, we have the kinetic energy. For that we need the velocity, because we know the kinetic energy is half mv square, right? So we need v. So to find v square equals to u square minus well, he's falling, so plus twice z, and then change in displacement twice gs. So his initial velocity was 0, so that goes to 0. So the final velocity v becomes square root of twice g, and his travel distance is half of the total distance here, h. So he traveled half, so we'll put z by 2 to cancel out, so we have left with square root of gh. So our kinetic energy would be half m, the mass, which we can say m is also equals to w by g, right, multiplied by square root gh whole square, because velocity is whole square root of gh, and then my mass is weight over g. Now if this let me use a different color. If we this square and square root cancel out, you can also cancel out this z, so we will be left with half wh, and this is our kinetic energy. So what is the potential energy? Because we need kinetic and potential. So potential energy at position 2, let me use a different color then. Potential energy, which is weight plus distance. So at this position 2, our paratrooper here, you will have potential energy W. So let's say potential energy, and this is our kinetic energy, W into the available distance h by 2, so which will be WH over 2. So again, at position 2 we have the total mechanical energy. If we sum these two, this kinetic and this potential, half WH over 2, so this will be at position 2 half WH plus half WH equals to WH, which is for position 2. So you see this WH is equal to the WH over here, which was for position 1. So what it tells us that even the paratrooper moved from position 1 to position 2, the total mechanical energy, sum of them, the sum of total mechanical energy and kinetic energy is always the same. In this case it's WH, and it's same from 1 to 2. Now let's see if we can see another scenario where we go to the last position, which is position 3, and let's see how what we get for total what do we get for total mechanical energy. So okay, for position 3, which is at the ground, and he is tired and he's looking red, the paratrooper. So again, total mechanical energy at position 3, E3, it will be 1, right? E3 equals to sum of the kinetic and potential energy. So at the ground, we assume he's at the ground, so there is no height left for our paratrooper. So the potential energy W plus H, no height, so H would be 0, so it means no potential energy. So the potential energy, kinetic energy plus potential energy, this potential energy goes to 0. So we have the maximum kinetic energy, and the velocity of this we can found is by, again, half m equals to W over G plus our velocity square root of twice GH, because last time we had H over 2, now we have the full height, so it's H, if we whole square. So if we cancel out this whole square root and we go we take off, and we can also cancel out this 2 and this 2 and this G and this G, we will be again left with WH. So we see even at the ground the total mechanical energy is WH. So in all the cases, position 1 to position 2, position 2 and to position 2 to position 3, all the scenario we have the total mechanical energy is WH. So what happened? At position 1 we had the maximum potential energy, that is WH, 0 kinetic energy. He fall down from the plane to the ground, his all potential energy is converted to kinetic energy, and at the ground the potential energy is 0, but the total sum is always WH for this system. So this is how we conserve the energy, and in the process by converting the kinetic potential energy into kinetic energy. So this is the example for conservation of energy. So that was our goal for today. Before we stop, there's one more thing to study, to talk about, is the what if there was a system of particles. So we talk about only one paratroopers, right, of particles. So what if the paratrooper also is carrying a load with him? So if there is more than one particles, what we have to do is that we have the conservation of energy equation as T1 plus V1 equals to T2 plus V2 for if there is more than one particle, all we have to do is that do the summation of initial kinetic energy, summation of initial potential energy equals to summation of final kinetic energy plus summation of final potential energy. So this is the same way. If there is more than one force, what do? We take the summation of the force. Same here. If we have more than one particle, it's a system of particles, then we just sum each of those together, and we'll have our conservation of energy. So that is it for today. We're gonna solve problem, and we just finished our chapter 14. Yes. Next lectures we're gonna move to chapter 15, and we're gonna solve problems. And if you have any question or you need more clarification on any part, just comment below and I'll explain that part, and if needed I'll make another video on that specific part that if you don't understand. But feel free to make comments and subscribe the channel because there will be more and more video uploaded and you'll be notified on that. So thank you. See you in the next lecture.